Good morning, everyone. Welcome to my talk. I'm Soyoung Kim. In this time, I'd like to introduce my recent work A-Cube, Adaptive Autonomous Allocation of TSCH slots. This is the joint work with my collaborator Hyungshin Kim and my advisor Jongwon Kim from Seoul National University. I worked for this research when I was a graduate student of Seoul National University, and now I am working at Samsung Research after graduation. I hope you enjoy my talk. First, I'd like to start the introduction with TSCH. Time-slotted channel hopping, called TSCH, is a MAC protocol that is based on time synchronization and channel hopping techniques. This is one of MAC modes defined at IEEE 802.15.4e standard. It was originally designed for industrial automation, so it provides high reliability and energy efficiency. Due to these strong advantages, it is also used for various purposes including smart city, healthcare, and public safety. On TSCH network, each node just follows prearranged schedule table. According to the schedule, it listens or transmits or sleeps. This is a schedule table. In TSCH, we call it as a slot frame. Its x-axis is time offset. In general, a duration of a time slot is 10 milliseconds. A node pair can exchange only one data packet and its corresponding acknowledgement in a time slot. Y-axis of slot frame is channel offset. This is an example of node B's activity schedule, and the schedule repeats over time. Slot frame scheduling directly affects network performance and communication efficiency. TSCH scheduling methods are categorized into centralized and distributed. With centralized scheduling method, a central node collects all the network information and takes global view, so optimal scheduling can be created. And the central node distributes its node's schedule over the network. If the network topology is changed due to a new node join event, a central node should repeat this process. So, this method lacks flexibility and scalability, with high traffic overhead. With distributed scheduling method, scheduling agent is distributed to other nodes. For example, a node pair exchanges packets to negotiate its future behavior for communication. So, it has higher responsiveness to a sudden topology changes. However, it still suffers from traffic overhead. There are another scheduling methods categorized into autonomous schedulers, where each node schedules its own slot frame without any negotiation process, not generating traffic overhead. Orchestra is the first autonomous scheduler. The key idea is simple. It utilizes the fact that each node already knows its RPL neighbors and their node ID, such as MAC address. It hashes node ID, and the hashed value is directly used as a time offset. If there is a new node join event, the new node calculates its own slot frame by hashing node ID. Due to its simple and light features, it has become one of the most commonly used scheduler in TSCH. Another autonomous scheduler called Alice handles directional links independently. It hashes link ID and time together to schedule slot frame and more efficiently distributes traffic over time and channel. It also introduced time-varying scheduling, which changes the schedule over time. We evaluated both Orchestra Analysis performance using 61 nodes. Here we enhanced Orchestra by introducing Alice's several features such as multiple channel offset utilization and time-varying scheduling method. At the fixed traffic load, we increased the slot frame length from 20 to 80. As the slot frame length increases, packet delivery ratio decreases drastically. At the long slot frame length, the transmission queue increased due to the lower transmission opportunity, and packets are dropped showing high queue loss number. The fundamental problem is that both schemes allocate fixed number of slots regardless of the slot frame length. To solve the problem in an efficient way, we need this traffic load awareness for adaptive scheduling. Simultaneously, we should preserve the autonomous feature, which makes autonomous scheduler most widely and commonly used these days. In this paper, we propose A-Cube, Autonomous Adaptive Allocation of TSCH Slots. This is an independent module that can be used with any autonomous scheduler. The basic concept of A-Cube is simple. Each node observes the utilization and the result of its own transmit and listen slots. Then, the sender knows its average transmission attempt rate at transmission slot, and the receiver can estimate the sender's transmission attempt rate by observing the results of listen slots. Based on this information, sender and receiver adapts the number of transmission and listen styles without any control packet exchange. Let's see the example based on LS schedule. You can see the red arrows indicating the link BA. Basically, A-Cube schedules one default slot per each link in a slot frame. Let's assume that the current transmission attempt rate of the link BA is 0.4 and the receiver's estimated value is 0.39, and both sender and receiver allocated one slot for the link BA. As traffic load in the link increases, the sender's transmission attempt increases. Also, the receiver's estimated value of the sender's transmission attempt increases. When the receiver's estimated transmission attempt rate reaches to 0.65, which is the receiver's increase threshold, it doubles the number of listen slots for the link BA, and the receiver adds a new listen slot on its slot frame. Now, a node A has 2 receive slots for the link BA, and its transmission attempt rate at the receive cell becomes half. As the traffic load increases, the sender's transmission attempt rate reaches to 0.75, which is the increase threshold of the sender. Then it doubles the number of transmission slots for the link BA and allocates more transmission slots for the link BA on its slot frame. And the transmission attempt rate decreases in half. Now, the sender and the receiver has 2 slots for the link BA. As we have seen before, A-Cube increase and decrease the number of slots based on the transmission attempt rate of the link. By using EWMA, the transmission attempt rate updates over time, and the range of the value is between 0 and 1. When the transmission attempt rate exceeds the increase threshold, we increase the number of slots by twice. When the transmission attempt rate is below the decrease threshold, we decrease the number of slots by half. Here, we set the receiver's increase-decrease threshold lower than the sender's thresholds to avoid cases where the sender transmits while the receiver is not listening to the channel. To keep autonomous feature, the sender and the receiver of the link cannot communicate, so we use hash function to decide the location of the slot. In this example, we assume the RPL topology as described in the figure. There are 8 nodes and 3 links need more slots due to high traffic loads. This example shows the zone selection mechanism and assumes the maximum number of slots allowed to have is 2, which becomes the number of zones in a slot frame. Then, we divide the slot frame into 2, which is the number of zones as described in the figure. At the first, only one slot is allocated for each directional link, and the hash function is used to select the primary zone where the default slot of the link is scheduled. Thereby, each node has different primary zone and default slots are distributed over slot frame. Based on the real-time traffic load, the sender and the receiver adaptively increase or decrease the slot number in an autonomous way. Newly allocated slots are scheduled at the secondary zone to well distribute traffic over slot frame. The novelty of A-Cube is straightforward. As far as we know, this is the first work that proposes a fully autonomous and real-time traffic load-based adaptive slot allocation scheme for TSCH scheduling. As an independent module, A-Cube can be applied to any autonomous TSCH scheduler such as Orchestra Analysis. We evaluated A-Cube on a real testbed. We implemented A-Cube on Contiki, and A-Cube code is available at GitHub. We used IoT Lab public testbed located at Grenoble, France, and used 61 IoT Lab M3 nodes. This figure shows a snapshot of a dynamic RPL topology during the experiment. I will share some of the results in this presentation. In this experiment, we evaluated performance by traffic load. We fixed the slot frame length that best fits for Orchestra Analysis and increased the traffic load from 4 to 10 packets per minute. Y-axis represents PDR, latency, and radio duty cycle. We compared the performance of Orchestra Analysis without and with A-Cube. We used two maximum zone numbers, 4 and 8. Without A-Cube, both Orchestra Analysis show poor performance as the traffic load increases. However, with A-Cube, both schemes consistently show higher PDR utilizing more slots. When we allow A-Cube to utilize up to 8 slots per each link, it achieves higher PDR with more communication opportunity. Also, A-Cube reduces latency, and it shows that the use of A-Cube does not increase the radio duty cycle much, as it allocates more cells to the only nodes with high traffic load. In summary, A-Cube achieves higher PDR with lower latency at the similar radio duty cycle, achieving both reliability and efficiency. In this experiment, we fixed the topology to observe the number of slots over time with A-Cube. Here, 61 nodes generate 2 packets per minute to and from the root node. The special 21 nodes marked with red circle generate packets with different traffic load over time. They change the traffic load as described in the red box. The first graph shows the number of slots for the link AR. The second shows those of the link BA, and the third shows those of the link CB. Blue and red lines show the number of transmission and receive slots respectively. At the time the traffic load changes, you can find the number of slots for the link AR changes according to the varying traffic load. This experiment achieved 99.9% packet delivery ratio. This is the conclusion. In this paper, we proposed A-Cube. This is the fully autonomous traffic-aware scheduling method. With A-Cube, any autonomous schedulers such as Alice and Orchestra can have traffic awareness maintaining autonomous feature. Our future work is comparing the performance of A-Cube with non-autonomous traffic-aware schedulers such as Tesla and OST. We believe that A-Cube could be the stepping stone for other researchers. As I mentioned before, A-Cube source code is open, so feel free to use A-Cube. Thank you.